Hello, my people. I hope you're doing well. I also hope that our time together earlier this afternoon was fruitful. I'm going to go ahead and continue on working through some of the problems in this, for lack of a better word, review packet that I've sort of cobbled together from pages of old tests. You might recognize these problems. These are the ones that I've already done. I'm going to start flipping through and working some of the problems I haven't done, and of course some of the problems that I also have not gotten to yet. I don't know how many videos I'll make of this. I'm going to keep going until I feel like I have given you a sufficient amount of review material so that you can feel confident studying and then of course taking the test. Let's go ahead and get started. I skipped over a couple of questions. While this one down here, number 3, is almost identical to the one on the previous page, because of course the one on the previous page was from a different test. All you would have to do to make it like the one on the previous page is simply to pull the 1/2 out in front, and then you get exactly the same integral. This one up here, however, is an antiderivative problem. First derivative with a single initial condition from the original function f. And if I anti-differentiate, I know that you can do it by recognizing the fact that x cubed becomes x to the 4th over 4, and then of course 3x squared becomes x cubed plus c. You could also recognize the fact that f prime can be sort of split up into 2 times 4x cubed, so that you don't have to do the fraction right here. 4x cubed is obviously already a recognizable derivative that can be anti-differentiated. But now that I have this, let's go ahead and simplify down to 2x to the 4th plus x cubed plus c. I notice that my ordered pair here is 2, 0. So if I plug in 2, I'm going to get 0 as an output. And I get 2 times 2 to the 4th, that's 16, plus 2 to the 3rd, that's 8, plus c. Now that would be 32 plus 8 is 40, so c is going to be equal to negative 40, and therefore f of x should be 2x to the 4th plus x cubed minus 40. And that should be our answer. Okay? Now we've done enough of those, so let's go ahead and move on. We briefly discussed how one would work through this, but let's go ahead and then work through it. In order to separate the fractions, and I'm not going to skip steps here, I'm going to go ahead and basically write it out exactly like I told you to do it. First step is to get it to here, right? Pull apart into 3 separate fractions. And then from there, I need to go ahead and simplify. That first one, x cubed over x, simplifies into x. That second one simplifies into 3 over x, or if you want, you can call it 3 times 1 over x, so that the 1 over x is all by itself, and of course we're going to recognize that as the derivative of natural log. Minus 4x to the negative 2, because unlike 1 over x, I'm going to use the power rule for that particular term. So as I go through it, I can now see how each of the terms is going to be integrated term by term. This is going to be 1/2 x squared plus 3 natural log of the absolute value of x. And then as I do x to the negative 2, I'm going to add 1 to it, meaning x to the negative 1, over negative 1. Now that negative 1 is going to cancel with this negative out in front, and I'm going to get plus 4 times x to the negative 1 plus c. And this should be your integral. Remember, the absolute value of x is important because you need that in order to match the domain of the 1 over x here for the original function. All right, let's go ahead and flip on over. We skipped this one because we did a Riemann Sum problem similar to it on the previous page, and of course that was a test problem from a previous year. For here, it's roughly the same thing, except for instead of, let's see, on the previous one, we were looking for right-hand Riemann sums. On this particular one, we're looking for midpoint. But it's still 0 to 4, and it's still 4 subintervals, and it's still a function that actually has a 0 at 0 and 4. So you'll see the fact that I have a type in terms of the kind of problems that I like to give. I just like them to be, you know, not too difficult to actually discern what the values are that we're trying to deal with. Now, 4 subintervals from 0 to 4, again, we're going to be dealing with the units 1, 2, 3, and 4. So 1, 2, 3, and 4. And of course, the midpoints in there are going between 0 and 1. The midpoint is going to be 1/2. Between 1 and 2, the midpoint is going to be 3/2. Between 2 and 3, the midpoint is going to be 5/2. Between 3 and 4, the midpoint is going to be 7/2. And we're going to use those values to designate the height of our subintervals. So let's go ahead and draw lines across showing where those heights what those heights have come to. And then we'll go back and draw the sides of the subintervals. Okay, this winds up being looking something like this. The reason why I want to draw the tops before the sides is just the idea of sometimes I draw the sides too far because I'm, you know, in the midst of drawing it, I'm thinking of a left hand rather than a right hand or a midpoint or something like that. And just make sure that it's all nice and pretty. And of course, you know, the most important thing in math is it's got to be pretty. Yes, I'm joking. Okay, let's go ahead and just for the sake of being able to see it, I'll go ahead and fill it in this colored highlighter pencil. And as you can see, it looks almost like the under and the over are actually in pretty good balance. So this may actually be a pretty good approximation. We'll check it when we're done, okay? But in order to arrive at, let me go ahead and zoom in a little bit more. I think we'll be able to see it a little bit better. We basically need to evaluate right here. This value is, of course, f of 1/2. This value is f of 3/2. This y value is f of 5/2, and this value is f of 7/2. Now, the width of all of these is a common width. So our area approximation is going to be 1, that common width. I'm not going to make the same mistake as I did last time, catching myself. And basically then it needs to be f of 1/2, f of 3/2, f of 5/2, and f of 7/2. Now, I could do that by hand. But in an effort to try and acquaint you better with your calculator, here's what we're going to do. I'm going to turn off the overhead light so I don't get as much glare. Okay. What I'm going to do is I'm going to go ahead and plug this function into y1. So I have 4x minus 1/4 x cubed. Okay. Now, I have that function, and these are the function values that I need to evaluate. So I can go back to the main screen. Remember that your y1 through y10 are here with the alpha f4. I'm going to take y1, and I'm going to use it like function notation. And for the sake of not having to push the buttons too many times, I'm going to just go ahead and use the decimals. And so it's y of 1/2, y1 of 1/2, and then y1 of 1.5, and then y1 of 2.5, and then y1 of 3.5, I need parentheses there first, 3.5. Enter. Now, of course, if I had anything other than a width of 1, I would of course be multiplying that sum by that common width of my subintervals, but I don't. And so it winds up being 16.5. 16 is, so it's 16 and a half, and so it's 33 halves would be the approximation. Now, since I already have the function loaded into my calculator, let's go ahead and do the integral in order to see how good that approximation is. Now, since it's already into y1, I can, for the integrand, actually just plop in y1. All you have to do is just make sure that your dx, that your differential right there matches the variable for what you're putting in the integrand. And of course, in y1, the variable is always x. And then I'm going to press enter. And it actually is 16. So I'm only 1/2 off, okay? And of course, this is a polynomial function. I actually could have done that by hand pretty easily, but seeing as that wasn't the point, I simply wanted to see how good the approximation was, and of course, to continue to acquaint you with your calculator, I went ahead and did it by the calculator. Now, let's go ahead and let's move on to the next problem. This is yet another one, okay? This one is like the previous one that we did earlier today. This is a right-hand sum of 4 subintervals. Now this one, of course, goes from 0 to 2, but it's still the same principle, okay? You're going to have 4 subintervals, so instead of each subinterval being a width of 1, you're going to have subintervals that have a width of 2, okay? Or width of 1/2. So what we want to do is obviously goes to 1/2, 1, 3/2, and so from 0 to 1/2 is your first subinterval, from 1/2 to 1 is your second subinterval, third subinterval, fourth subinterval, and I'm using the value on the right-hand side to define the height of each of those subintervals. So again, like the first one that we did, the one that we did during our session, during our 2 o'clock to 3 o'clock session today, the height of this last subinterval is going to be 0. It happens, not a huge deal. Let's go ahead and draw this so that we can actually see those subinterval heights and actually see the boxes. Now, obviously, the fact that this height right here for the fourth subinterval is going to be 0, that fourth subinterval is going to be an underestimate, right? The question is, seeing as these two are overestimates, and this one's kind of split, are these two overages going to compensate for this underestimation? And of course, we can go ahead and check that out when we're all done with it. Let's go ahead and fill it in so that we see it a little bit better. Okay. And I'll tell you what, just to make sure that we can see the function, I'll go ahead and use a Sharpie to darken it up just a little bit. Okay. Now, we know that basically f of 1/2 is going to be the height of this box, so that's 1/2 times f of 1/2. You know that the height at f of 1 is going to be this one, so the area of this second rectangle is 1/2 width times f of 1 height. Third one, again, width of 1/2, height of f of 3/2. So my area estimation is going to be 1/2 f of 1/2 plus f of 1 plus f of 3/2 plus f of 2. Now f of 2, of course, is 0, so it's inconsequential in terms of actually evaluating all of this. We can go ahead and plug it in if we wanted to. This actually is a pretty easy function to evaluate since it actually, since we can simplify it. So you have f of x is equal to 2x squared minus x cubed, in case you don't like that negative leading coefficient, I can go ahead and factor out an x squared, and I get 2 minus x. So actually plugging in these values isn't going to be too much of a chore. But again, let's go ahead and use our calculator, simply because we can. Okay, actually, I guess that was already. Let's go ahead and turn it off, and let it readjust for a second. Okay, let's go ahead and clear out the one from the last problem. So we have negative x cubed plus 2x squared. Let's go ahead and go back to the home screen. Now, I know that it's going to be 1/2 times this, and you can go ahead and just get this sum and then multiply by 1/2, but you risk forgetting to do that, okay? So you may want to, and I'll go ahead and use the fractions now, 1/2 times y of 1/2 plus y1 of 1 plus y1 of 3/2. And just for the sake of just being exhaustive, despite the fact that I know that it's 0, let's go ahead and plug that in. And now I have all of the pieces, and I'm going to press enter, and the area approximation, the area of those 3 rectangles, is going to be 5/4. Now, just for giggles, let's go ahead and see what the actual area is. Okay, y1 of x, and okay, that's not too bad. So this is 1 point, in terms of a decimal, that's 1.25. The actual area is basically 4/3, right? 4/3, or 1.333, okay? So that's not too bad. So, minus 1.25, okay? And of course, you could get a common denominator. Oh, by the way, just in case you want to know, the way that you would change it from fraction to decimal and decimal to fraction, that's what that means right there under the alpha F1. So if you wanted to change this decimal answer to a fraction, it's 1/12. Okay. Now, let's see. How long have we been going on this? Okay, we've been going for a little over 17 minutes. Let's see what we have in store. Let's do number 7, and then I'll call it quits on this video, and I'll probably start another one in order to get through a few more problems. Now here, this is the page for the fundamental theorem of calculus, and we're trying to find the area under the curve. Not that difficult. We simply need to evaluate the integral of this function, negative 1/4 x squared plus 4 dx. And when I do that, of course, this is a polynomial. We've done term by term. We get negative 1/4 times x cubed over 3 plus 4x, right? And I'm going to evaluate this from 0 to 4. Let me go ahead and clean that up just a little bit. That's negative 1/12 x cubed plus 4x from 0 to 4. And it really doesn't matter where you put the parentheses, just as long as you have that little thing right there. This is probably more correct, but I'm not really interested in that right now. Now, when I cube 4, obviously when I plug in 0, this is values that's going to be 0. So really all I'm interested in is the 4, right? When I plug in 4 cubed is going to be 64. Of course, 4 cubed is also 16 times 4, whereas this denominator is 3 times 4. So really you get negative 16/3. And then, of course, 4 times 4 is 16, and that means you wind up with 32/3. Okay? Remember, because if you get a common denominator, this is 48/3, negative 16/3 plus 48/3, 32/3. Okay? Let's go ahead and call it quits. We'll go ahead and start here on more fundamental theorem of calculus questions in the next video.